I wanted to show you first is this. So we'll talk about oscillations phenomena, we'll talk about wave propagation. All of you experience it. We all live in California. This is one of the ways we experience vibrations, which can be quite destructive. This is a simulation of a earthquake that happens in Eureka, here somewhere, which may happen in Eureka at some point on San Andreas Fault, which we all know and love. Well, we here live right on Hayward Fault. Right, it goes right into the Memorial Stadium, which is one reason the Memorial Stadium was retrofitted a couple of years ago to make it safer. This simulation from Berkeley Seismological Laboratory that works on early earthquake warning systems. The systems that actually now, I'll talk a little more about this on Thursday, but these are the systems that are supposed to provide you a warning early enough before the actual, not before the earthquake hits, that's difficult, but after the earthquake hits somewhere else, at the epicenter here in Eureka, the system is supposed to provide you and the critical infrastructures with the critical warning a few seconds to a few minutes before the actual shaking happens. This is how the simulation works. Let me see. There we go. So suppose the fault happens. The rupture on the San Andreas Fault happens near Eureka, and you see waves propagating, radiating outwards from the epicenter. This is the simulated magnitude 8 earthquake, similar to what happened in 1906 here in San Francisco. And what you see is the waves propagating outwards. There are two colors, yellow and red. Yellow is the P wave, the primary wave that has the velocity of about 6 kilometers a second, and that approaches San Francisco Bay Area first. It's the highest speed wave. The epicenter is about 500 kilometers away, so it hits the San Francisco Bay Area first, sort of a minute later. You can see on the bottom graph the magnitude of vibrations. At some point, these P waves are relatively low, and so at this point, you're now maybe feeling some vibration. They're not violent yet. A bit later, the first S wave shows up. This is where you start feeling a little uncomfortable in your seats. Maybe the lights shake a bit more. The magnitude of vibrations increase suddenly. This is the time to get onto the desks, which you don't have. And then more intense vibrations come, and as you also see, the distance between the fronts decreases, the waves tend to pile up, and the magnitude of vibrations increases more. You start feeling the shakes. What you also notice is that in fact, things happen here. You see that the fault itself ruptures along the fault direction, and that in fact increases the magnitude of destructive force closer to us. Because as the wave propagates, so is the source. And so you see these wavefronts piling up. This is exactly what we'll talk about later this week on Thursday, called the Doppler effect. This is the compression of the wavefronts and the reduction in the wavelengths, or increase in the frequency that you see because of the propagating wavefront. And so this earthquake does reach, in this simulation, significant magnitude above the destruction threshold, damage threshold, and then at some point the intensity decreases. So we've now lived through this for the next 2 minutes, or for the previous 2 minutes. Hopefully, if the real one hits on San Andreas Fault or on Hayward Fault, we'll be prepared. One thing to notice, though, is that this whole process does take a while. I was talking for 2 minutes or 3 minutes. In the meantime, you could have gotten up, run out of the door as the first timer started, Or you could have looked at your cell phone. It could have started flashing, telling you that the earthquake is about to hit, and you're supposed to protect yourself. And this is, in fact, the system that this center here on campus is developing. The early warning system that's supposed to notify the consumers, that is you, but also notify places like BART, notify places like power plants and other critical infrastructure units of an impending disaster with significant potential for damage, and therefore try to prevent it by shutting something down safely or telling the citizens to hide under something sturdy. So exactly how this works is in fact the subject, how the early warning systems would work and how the waves propagate is exactly the topic of our discussion this week. You guys have any questions about this? Well, hopefully we will not live through, well, hopefully we will live through this, hopefully we will not experience magnitude 8 here in the Bay Area. However, we do need to be prepared. Various estimates state that the probability to get the big one here in the Bay Area is quite high. It's almost certainty, well, 2/3 probability in next 30 years or so of a magnitude 7 or higher earthquake, with 1/3 probability to be for this earthquake to be along San Andreas Fault, which is this one, and another 30% probability to be along Hayward Fault, which is this, and the Hayward Fault is right under our feet. In fact, there was an earthquake here on campus, I think 3 years ago. Any of you live in Clark Kerr campus? Yeah, there was one about 3 years ago right underneath Clark Kerr. It wasn't Hayward Fault, it wasn't that significant, it was I think magnitude 4. As it turns out, physics department had a retreat during the earthquake. We were sitting right in Clark Kerr campus, and things started shaking. So we live in earthquake country, understanding how to design early warning systems, understanding how they work, understanding how much time you will have if you receive this warning, how effective these warning systems are, and what to do is important. But again, chances are, unless you move out of the area, you will experience some earthquake activity in your lifetime. So what we will talk about this week is vibrations, periodic motion, which, as it turns out, is the most common motion known to science. In fact, almost all of the phenomena we look at exhibit some kind of a periodic behavior. Motion of electrons around nuclei, somewhat periodic, although as we'll discuss when we talk about quantum mechanics, also has a lot of randomness to it. Every morning you wake up, hopefully, and you experience periodic motion without knowing this. Your heart beats, hopefully periodically. The period may change depending on the activity, but at any given moment, it's periodic from 60 beats per second, or the value which we describe frequency of about 1 hertz, or maybe a little bit faster. If you are swinging on swings, a child swing is an example of a periodic motion. It's called the pendulum. You may have seen very large pendula, large, masses on strings in various museums, or like there's the big pendulum, for example, in the I think there's one in California Science Center. There's one in the hills. There's this observatory in the hills. I forget what it's called. In the Oakland Hills, Chabot. Yes, Chabot Observatory. I think they have the Foucault pendulum there that demonstrates rotation of the Earth. If you put something on a spring, any mass on a spring vibrates. This is another example of periodic motion. pretty much any, well, you know, another string can vibrate. Pretty much any physically large object will have some elasticity to it, so it will be springy to some extent. Almost any object known to science will have a mass. And so most objects we know will have some kind of a oscillating periodic motion associated with it at some frequency. And we'll discuss that too. You know, every building, every bridge will have a specific frequency under which it will vibrate relatively violently. If excited at that specific frequency, this is the phenomenon known as resonance. And again, we'll show examples of that. So pretty much all around us, strings, atoms, human heart, human brain activity are governed by periodic motion. The only things that don't, well, you know, motion of planets around the sun, motion of satellites around the Earth, rotation of the Earth around its axis, rotation of the Earth around the sun, are all again examples of periodic motion, not necessarily oscillations, but something that happens over and over again at fixed intervals in time. And this is what we call periodic motion. You know, if you want to be mathematical about it, we define periodic motion in terms of this characteristic time interval between the same events. So if something happens at exactly the same time intervals over and over again, your heart beats hopefully once per second repeatedly, and if you're not too excited, this, if you're laying in bed, let's say in a sleep, your heart beats at exactly the same rate for minutes to hours. This is a periodic motion. So what the graph shown here is one example. If you plot some, you know, some quantity that happens over and over and over again, say displacement of this mass relative to its normal position, so-called equilibrium position when this mass is not moving, I can plot this displacement as a function of time. And if I observe that this mass occupies the same position at fixed intervals in time over and over and over again, I'll call this a periodic motion. And then the time interval over which the pattern repeats itself is called the period. If I take the inverse of that, we'll call that frequency. So if the period is measured in the time units, minutes, seconds, years, then the inverse of that frequency is measured in, obviously, reciprocal units. And in science, these are called hertz. The unit is named after a German physicist who was studying periodic effects like this. He was actually the guy who first produced electromagnetic waves and observed their propagation. Possibly producing X-rays in the process without realizing this. So when we talk about frequency, we'll talk about these units, and I'll mention those hertz. Hertz are beats per second. Second is a convenient human unit. 1 hertz is roughly the frequency of your heart if you're at rest. Say 20 hertz is the frequency that you can barely hear. You know, we'll discuss sound. Sound is an example of vibrational motion of molecules impinging on your ear and vibrating your eardrum, that then gets transferred to little electrical signals that are sent to your brain, and we perceive that as sound. Frequency of 20 beats per second you can barely hear. In fact, this is not it. I have a little tone generator here. I can play to you sounds that vibrate at various frequencies. This is 20 hertz, and you can hear it. Well, admittedly, the speaker isn't great. Your perception depends on how well you hear and how good the speaker is in transmitting this vibration. In this case, this speaker probably isn't that great. These are vibrations of 60 beats per second. You often hear this. If you're driving somewhere, say listening to an AM station, and every once in a while you hear this noise. This is the pickup of your radio antenna from a power line, most likely that's nearby, and it sounds like this. This is the sounds of electrical interference. This is 60 bits per second. This is how your electrical outlet would sound like if you were to put a speaker to it. Everybody should turn their cell phones, right? Off. This is the sound of 1,000 bits per second. Pretty annoying. This is, I suppose, how a little mosquito would sound like. Well, maybe a little higher. Mosquitoes are even more annoying than that. Maybe like this. This is a mosquito. This is 10,000 bits per second. And if I'm really annoying, this is the sound that I cannot hear, but some of you might, of 20 kilohertz. Can hear. Oh, if you actually have a good speaker, you know, plug the speakers into your phone. This, you know, the headphones. Good headphones will actually transmit sounds up to 20 kilohertz. Although often they would start cutting off around 18. Well, maybe this is near the edge of perception for these particular speakers. Yeah, I know. My apologies. This is 15,000 hertz. So these are perceived vibrations, perceived sounds. We'll get back to that a bit later today. So one example of this motion is so-called harmonic motion. This is possibly the only piece of math that you'll see. I will not test you on this piece of math, but for those mathematically inclined, and if you have taken trig at school, you have seen this function called cosine. It gives you oscillations whose dependence on time is very smooth and kind of very harmonic, looks nice. It not only looks nice, it sounds nice. This is how this sounds. This is the purest form of vibration known to physicists. This is called harmonic motion that describes by one particular frequency and nothing else. Here is how it sounds. No, this is not how this sounds. This is the piano. I want a whistle. 59. Can you switch to oscilloscope, please? In the booth. So again, here in the booth, I have here on front, I have a device called the oscilloscope that will actually show me that's it. The trace of sound vibrations as a function of time. I have a microphone here, and so right now you are looking at the trace of my voice, digitized at very short intervals in time, digitized on the horizontal axis here in the units of 1 millisecond. One box here, a box like this, is 1/1000th of a second or 1 millisecond. So if you see vibrations that fill one box like this, these vibrations happen at a frequency of 1/1000th of a second, or 1 kilohertz, 1,000 hertz. So as you hear me speak, you see this trace oscillate up and down. And so you can see that my voice has the typical period of larger than one box. So that means that I speak with the frequencies that are smaller than roughly 1 kilohertz, and I know, is it called a baritone, right? Somewhere maybe a little bit higher than that. So, my typical frequencies are between maybe 300-400 hertz. But I can play a tune at a higher frequency. This is roughly the frequency of a kilohertz. And so you see vibrations that are very smooth, very periodic. And these are called harmonic vibrations or harmonic motion. And if I play a tune that's at a lower frequency, like this, you see the pattern spread out, the period of vibrations is larger. You can count how many boxes, about 5 in this case. So the period is about 5 milliseconds. The frequency is 1/5 milliseconds, about 200 hertz. Well, this thing says, yeah, about 200 hertz. That's somewhere below a C. This is the higher frequency of a kilohertz. And I see even higher frequency, or maybe a couple. So the farther I go up the piano scale, the farther to the right, the higher the frequency. And again, we'll discuss that a little bit more. So again, sounds are a perfect example of vibrational motion, and we'll discuss the pure tones that, if you switch back to the screen, that describe this perfect sinusoidal or cosinusoidal trigonometric cosine-like vibrations, otherwise known as harmonic motion. Can we switch back to my projector, please? There you go. So I mentioned that a very important concept when we discuss vibrations is the fact that pretty much every solid body has a very characteristic vibrational frequency. This has basically to do with its size. And sometimes it has to do with its mass, sometimes it has to do with elasticity, but sort of to first order, everything has to do with the size. Size matters in certain things. This is a demonstration of this. If you have a pendulum, and if you are pushing a child on a swing, you have to push that child periodically in order to make them go higher and higher. This particular pendulum oscillates at a frequency of maybe slightly faster than 1 beat per second. This ball comes back to me sort of slightly faster than 1 Mississippi per beat, right? Slightly faster than once a second. I can decrease the length of this object, and you can see that it starts vibrating even faster. If I decrease the length of the pendulum will vibrate faster. If I increase the length, the pendulum vibrates slower. The frequency of vibrations depends on the size, depends on the length in this particular case. So every object has this characteristic frequency of vibrations that have to do with how it's built, have to do with typically with the size. So if I push this object just right, if I push this ball every time it comes back to me and stops, pauses momentarily, if at that point I push it forward, and I keep doing this, over time I will increase the amplitude of vibrations. It doesn't matter how strong I push. I can start weakly and keep pushing over time. If I do it exactly right, if I always push at exactly the right moment, that is, if I actually push exactly with the frequency with which this ball oscillates, over time I will build up a large amplitude. If I push at a different frequency, if I push kind of, let's say, at much higher frequency, no amplitudes, the amplitudes don't increase. If I push slowly, sometimes when the ball goes back to me, or sometimes when it's here, randomly, the amplitude doesn't necessarily grow. This is a concept known as resonance. If I excite the vibrations, vibrations can be either self-induced sometimes. They can be free. I can start the oscillations and just let the pendulum go for a while. This is known as free oscillation. I started at some point and then I let the object be on its own. You see that these vibrations go for a while. Eventually, these vibrations will die down. The energy associated with this motion will dissipate through friction, through interaction with the air, through friction of the string against its suspension, through various elastic motion. Eventually, the energy will dissipate and be lost, transformed into heat, as we all know. But these vibrations may go for a while. On the other hand, I can also produce driven vibrations, driven oscillations at some frequency. I can keep pushing. And so if I keep pushing exactly at the right moment, I can increase very large amplitudes. I can create vibrations that are very violent. So if I push repeatedly at exactly the right frequency, I can create, even if I push very weakly, but if I do it repeatedly over time, I can create large oscillations. So this is the phenomenon known as resonance. In fact, it can produce very large and very destructive effects. This is an interesting picture. This is some earthquake somewhere in Japan. You notice, earthquakes, you saw that demonstration, propagate with large velocities. P wave speed is about 6 kilometers a second, 4 miles a second. S wave speed is about 4 kilometers a second, call it 2.5 miles a second. They propagate quickly, they spread over a large area. So the amplitudes of vibration of the ground don't vary significantly over scales of hundreds of meters. This building is probably about 100 yards away from this building, and yet, for the same earthquake, this building was demolished and this one stood. Yet, the vibrations were exactly the same. Frequencies were about the same, amplitudes were about the same, and then one building got demolished, the other one didn't. Difference probably was that this building exhibited by very large amplitude vibrations that probably experienced a resonant effect. Here's another example of the same effect that we actually teach in every introductory physics course. This is the standard example of a resonance in a large structure. In this case, Tacoma Narrows Bridge. This bridge was built in the early 40s. I guess it says it was opened for traffic on July 1st, 1940. And it stood for a few months and then collapsed. This is the picture of what happened. As it turns out, the physics of this is somewhat more complicated than just automatic resonance, but the effect is nevertheless extremely pronounced and spectacular. So the bridge was open in November. Large winds caused a resonant effect that coupled to a torsional motion like this on the bridge. And you see the bridge oscillates at a very specific frequency. And over time, the amplitude of vibrations grows. The bridge keeps oscillating at the same frequencies. The winds keep blowing and keep exciting exactly the same vibration. It just so happens that these vibrations did not dissipate through friction quickly enough, and the bridge allowed these vibrations to grow more and more violently and build up over time in amplitude until the point where the structure of the bridge couldn't handle it anymore and the bridge collapsed. This is again, stereotypical example that we tell every engineering student in physics since 1940s of a wind causing a resonant effect on a large structure. You notice that these vibrations happened, the frequency of vibrations was fairly slow, very low, maybe a hertz or so. Again, it had to do with the size, transverse size of the bridge. It had a characteristic frequency of about a hertz, and as it turns out, the wind patterns in the Tacoma Strait, coupled to the relatively periodic structure of the bridge, produced the vibrations at exactly that frequency. The bridge design did not dissipate, didn't have enough friction, effectively didn't dissipate vibrations at that frequency well enough to reduce the resonant effect, and the bridge eventually collapsed. Luckily enough, nobody got hurt. Well, no people got hurt. A little dog died. You saw that car? There was a car on the bridge. Apparently, little dog got so frightened, didn't want to leave the car and perished in this disaster. That was the only fatality. Now, so as I said, these effects are known to men, to engineers, to physicists since 1940s. You would think that we would then incorporate good designs into designs of the bridge. We would sort of learn how to build bridges that don't vibrate at some specific frequencies, or at least bridges would dampen, they dissipate energy in the vibrations effectively enough. And sure, between 1940s and 2000s, we built a lot of bridges, well, engineers built a lot of bridges that still stand. We built spectacular bridges. One of them is this Millennium Bridge. It was built in London in 2000, just before the turn of the century. Before 2000, it was opened with great fanfare on June 10th, 2000. This is a demonstration of this bridge. You know, it's a pedestrian bridge, so it was open for foot traffic on July 10th. And people flooded it, and you notice it started vibrating at a very specific frequency. As it turns out, it also had this very specific frequency for the transverse motion. Actually, also slightly torsional motion like this. And as it turns out, if you imagine yourself on a boat, and if you're walking around and the boat rocks side to side, what do? You try to counteract that rocking motion. So what happens on this bridge is that the bridge was susceptible to torsional motion at one specific frequency. It started rocking side to side a little bit, and everybody started walking in lockstep to counteract that vibrational motion. That only increased the vibrations with the same frequency. It only increased this resonant effect. Everybody started walking at exactly the frequency of about 1 Hertz, exciting the bridge even more and more, and 2,000 people can cause significant vibrations. So this was uncomfortable. The bridge didn't collapse, luckily, with 2,000 people on it, but the British engineers quickly figured out how to reduce vibrations in this direction, effectively damping the vibrations, but also let everybody walk at different frequencies. So this bridge was reopened a few months later, and the problem was solved. So the British engineers were at least didn't foresee this, didn't see this coming, but at least were able to fix this. Compared to American engineers that lost the bridge. One would think that obviously, clearly, between after this, everybody in every engineering school would know about resonant effects on bridges and would know how to build them correctly. And of course, we teach in Russian schools the proper engineering designs too. Russians build good bridges. This one over the Volga River in Volgograd, formerly known as Stalingrad. There was a new bridge opened there in 2010. I don't think I taught anybody who built this bridge. I hope. This is how this bridge looked. Actually, it exhibited exactly the same behavior as the Tacoma Strait Bridge in 2040. It also started vibrating. In May 22nd, 2010, large winds over the Volga River excited exactly similar, very similar motion to the Tacoma Strait. It also had this resonant frequency of about 1 Hertz. And the wind coupled to, again, periodic structures on the bridge excited a vibrational motion on the bridge. Bridge was closed. Luckily, it didn't actually collapse. And a few months later, this bridge was reinforced to both make it sturdier, but also to dampen the vibrations at this specific frequency. But again, wind effects can be spectacular. So you can see it on YouTube. So again, these resonant effects can be important in engineering, can be important in civil construction. What you notice is that these objects, again, they are extended large objects, and they have these very specific frequencies at which they vibrate. And those vibrations have to do with the size. We'll talk about the standing waves on these bridges, perhaps on Thursday, or extended objects. So what those objects actually display is not a simple periodic motion, but a periodic motion of that has to do with the coupling on one side of the bridge to another, some effect called known as standing wave. And the way to understand it is the following. Oops, my apologies. So if you have a single pendulum, you can make it swing, make it go at some frequency. It will oscillate back and forth periodically. What happens if you have two pendula? Oh, I can make one of them oscillate. Suppose I have two masses on some rods, and I couple them by some spring, by some elastic object. And, suppose I push on one of them. Now it starts rocking back and forth. This object oscillates at some specific frequency. Now suppose I also let the other pendulum free. You notice that the vibrations propagate from one side to another. At some point, the left object oscillates, and then a little bit later, the right one, and then the motion moves back. So there's some kind of a delayed effect. The motion of the left pendulum gets transferred to the motion of the right with some delay. The motion propagates from left to right. Same thing can happen if I now connect three masses with springs. I can start the vibrations on one side, and over time, these vibrations will couple to the pendulum on the right. The object on the right will start vibrating, and at some point, the object on the far right will start vibrating. In other words, this elastic connection between the three masses propagates the vibration from one side to another. This is an effect known as wave propagation. This is exactly what creates wave motion. Wave motion is created whenever you have vibrations that are allowed to couple, allowed to connect from one side of an object to another due to elasticity, due to the elasticity of the medium. And so if you now connect an infinite number of such objects and start oscillating on one side, this vibration can propagate from one piece to another piece, to another piece, to another piece with some delay. And what you create is a propagating wave that looks something like this. I can start oscillations on this end, like this, and then let it propagate along the string, and you see this kind of a propagating motion. One side of the string will tug on another, cause it to move. That piece will tug on its neighbor, will cause it to move. This piece will tug on its neighbor, will cause it to move. And this motion will propagate along the direction of the string with some velocity. You see the motion propagating from left to right and then backwards with some speed. This is a characteristic speed of the medium known as the wave speed or wave velocity that characterizes how quickly the vibration passes from one side to another, from one little mass to its neighbor. This is characterized by this quantity v that's known as the wave speed. And then you can characterize the vibrations also by two other quantities that are very characteristic of these vibrations on an extended object. One is the frequency. The frequency typically has to do with how often I tug on the string. This frequency is smaller than something like this. So the frequency of vibration typically has something to do with the source. How fast I excite the vibrations. For example, which note I play, determines the frequency or the period of vibrations. This is this number. If I look at how the wave propagates, if it's a pure tone, pure sinusoidal tone like this whistle sound on the piano, the shape of the wave will look like this periodic sine wave function propagating both in time and in space. And so I can look at how often the same pattern repeats itself in time. We'll call this the period of vibrations. And I can also look at how often this pattern repeats in space. And this is known as wavelengths. The ratio of the two turns out to be characteristic to the medium that sustains this vibrational motion that propagates this wave. This is called the wave velocity or wave speed. And that's very characteristic of the medium where the wave propagates. For example, the sound propagates at very specific speed, very specific velocity in air. That's about 300 meters a second, or 9,900 feet per second, or the other way to express it is 1 mile for every 5 seconds. That's the propagation of the sound in air. If you propagate the same sounds in metals, it can be larger. This velocity is very characteristic to the medium where the wave propagates. Now, as it turns out, there are two types of waves we can look at. One is so-called transverse. This, in fact, is an example of a transverse wave where the displacement of the string happens in the direction that's transverse to the direction of the string. This is sort of a little bit odd, so bear with me. If you look at how each individual piece of string oscillates or propagates, does it move to the right with this velocity of, many meters per second? If I look at how the wave will propagate to the right, I make a displacement on the left side of the string and I let it go. We see the oscillation move back and forth. But at the same time, each piece of the string isn't moving to the right or to the left. Each piece of the string is only oscillating roughly in its place, but is going up and down. So this is a part of the wave motion that's often easy to misunderstand. The fact that in the vibrational motion, each individual piece doesn't actually travel along the direction of the wave with this large wave speed. Sound, molecules near my mouth do not travel to you. Luckily enough, if I had a flu, I could still talk to you and not, if we are separated by many yards or feet, not endanger you too much. Molecules from my air don't propagate to you, they vibrate near my mouth, and the pressure wave that builds up from my mouth propagates towards you. The vibrations of the air molecules relative to their normal positions propagates, while the molecules themselves stay near their place. Something happens for these transverse waves. Each piece of the string vibrates up and down, and this vibration propagates along the elastic medium forward or backward, like so. So whenever that happens, we call this motion a transverse wave, whenever the propagations happen in the direction that's transverse to the direction of the wave propagation. I have a model of the wave here, which makes it a little bit easier to see. You can look at each ball as a particular mass similar to the mass of this pendulum. Something has broken. There you go. So I can move each ball up and down. So focus, let's say, on this ball. You see that this ball will just rock up and down as I turn the crank. So each ball oscillates up and down, and these oscillations propagate to the side. The oscillations of the ball next to it are somewhat delayed relative to this ball. This ball oscillates in exactly the same way as the ball is its neighbor, but the oscillations are delayed by some amount. The oscillation of the ball next to this one are delayed by some amount. The oscillation of this ball are delayed by some amount in time. And so what you see is the pattern that repeats itself in space, but with some delay. The amount of time it takes for these oscillations to propagate over some distance is characteristic of the wave speed. Each piece of this wave oscillates in its place transversely, and the oscillation propagates forward due to the fact that the oscillations of each neighbor are delayed with respect to the previous object. This is an example of a transverse wave, where oscillations are in the direction perpendicular to the direction of oscillations. But one can also look at a similar motion. Oscillations can also happen in the direction of propagation. This is how sound works. When I move my tongue in my mouth, I produce a pressure wave that compresses the molecules of air. Those compressed molecules of air push on its neighbors, push them outwards a bit. Those push the molecules further out, further and further out, and you produce a wave that's so-called longitudinal, where the oscillations happen in the direction of motion. Sort of similar to that model, where each ball oscillates around its normal position, and you see density change from left to right, density propagate from left to right. So focus on each object. It oscillates around its nominal position, and this increase in density propagates from left to right. This kind of similar is what happens if you have an accident on the freeway, or a slowdown on the freeway, or another kind of a traffic jam. Suppose you're driving on the road and you see the car in front of you slow down, right? The red lights in the back hopefully turn on. You see that, it takes you some time to react, you push on the brakes. The guy behind you will see your brake lights, it'll take them some time to react, they'll push on the brakes. And the guy behind them will push on the brakes, and so this light of red lights will propagate backward. It takes everybody some amount of time to react, that takes some delay, and so this pile up, or the stops, will propagate backwards with some velocity. The density of the cars will increase as everybody slows down. And then maybe the cause of the traffic up front is alleviated. The car in the front of the traffic jam accelerates. Maybe the CHP cleared the road. They will start accelerating. The guy behind that car will have some time to react. They will accelerate a little bit later. The guy behind that will accelerate a little bit later, and you start to see that pileup dissipate. But it takes everybody some time to react, to accelerate, or to brake, and so you'll see this increase or decrease in density propagate forward or backward. That's another example of longitudinal propagation of a wave, longitudinal motion. And there are other examples. For example, so sound is an example of the increase or decrease in pressure along the direction of the sound wave propagation. P waves in earthquakes are called P waves, so otherwise known as pressure waves. They propagate also through the bulk of material by increasing or decreasing the density slightly. And there are the examples. So let me pause now for a second and actually see if you guys have read the book that discusses sound in particular and discusses the velocity of the sound waves. So here's the question for you. Suppose you are listening to the sound in vacuum, or you're listening to the sound in air, or you're listening to the sound in water. Which sound travels faster? If you're, let's say, does the sound propagate faster in water, in rock, in air, or in vacuum? I told you that the sound is a characteristic of the medium in which it propagates. So let's see if you remember how much the sound propagates with, and how fast it propagates in various materials. I'll start at the count, push the buttons A, B, or C, and then we'll discuss. I think I'll want to move this out for now. Okay, maybe 5 more seconds, and then we'll look at the results. Yeah, if you're using the clicker go, it takes a while. I'll give you maybe 10 more seconds. Are you done? Oh, all right. Last person. Okay, thanks. Oh, it just came in. So, let's look at the answers. Did it pop up? It did not pop up. Most of you think that sound propagates fastest in rock. That's the right answer. Interestingly enough, oops, no data available. No, I pushed the wrong button. Interestingly enough, there are 2 other options. Let me close this. So let's discuss this. First of all, does sound propagate in vacuum? Well, the answer is no. If you read sci-fi, there's this famous expression, I forget who, that nobody in space, nobody can hear you scream. I forgot who wrote that. Kind of a beautiful expression. This is actually contrary to most sci-fi. If you watch Star Trek, you watch Star Wars, in particular Star Wars, I was actually, wanted to put that clip in, but there's no point. Everybody watched Star Wars, watched, hopefully, if you remember, any Starfighter episodes, the attack in this canyon, right, on the Death Star, there's this, whatever they call, TIE fighters and the, rebel fighters, and they're all shooting at each other, and sounds go, pop, 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 right, and you can hear them. They dive, and they sound like the bombers, in the World War II. That's somewhat incorrect. If you're actually listening in space, you wouldn't hear any sound at all. And here's a demonstration. Sound requires an elastic medium to propagate. Sound is exactly the vibrations caused by pressure changes. So if there's no pressure, there's no changes. Therefore, no sound. Here's a demonstration of that. I have this annoying bell here, and when it rings, you are not to get up. It's not the end of the class yet. I have to actually see. Oh, these guys are connected. These guys will be connected. So this annoying bell rings easily in air. So hopefully I'll be able to make it also a ring. What happened? We had some electrical difficulties here. Oh, I broke the device. Well, you know what? We might have to repeat it next time. We had some difficulties today, and the wiring broke loose. What I was going to demonstrate to you, and I'll hopefully demonstrate to you next time, is that when I evacuate, I could have put a jar over this bell, pump the air out, and the sound would disappear. It's easy for me to describe, but I demolished the demonstration. I'll apologize to James. In vacuum, sound waves don't travel, unlike what's shown in sci-fi movies. But they do travel fast, and they do travel fast in solid. The sound waves do travel faster in solids than they do in air. And the main reason for this is the fact that the molecules in solids are much more closely spaced than the molecules in air. As you might remember from chapter 2, I think when we discussed heat, the density of gases is typically order of 1,000 times smaller than the density of solids or liquids. And the velocity of propagation depends on the density as a square root or as 1 over square root of density. You don't need to remember this formula. You just need to remember that the fact that the objects that are materials that are dilute, like gases, cannot propagate the vibrations as effectively as the media that dense. It's sort of easy to understand. In order for materials to propagate vibrations, in order for this wave to propagate, one end of the string has to tug on the other. And in air, one molecule has to somehow push on the other. If these molecules are farther apart, it takes them time to push on each other, it takes them time to propagate that vibration. Velocity is smaller compared to when the vibrations happen in a solid or liquid medium where the molecules are necessarily closer together. So the speed of sound in typical solids is larger than the speed of sound in typical gases. I'll show you a demonstration of that on Thursday. You know that if you inhale helium, the sound of your voice will tend to be higher. You'll sound like a munchkin. There's a reason for that. When we discuss standing waves, it will become clear. But the main reason for this is the fact that the velocity of propagation is larger in helium. The wavelength of vibrations is the same. The frequency tends to be higher. It is proportional to this wave speed. This fact, in fact, the fact that the sound propagates better, more effectively, and also faster in solids can be used. I wouldn't advise you to listen to the trains by putting your ear to the ground or to the rail, right? You can probably hear the impending doom coming to you quicker than if you were just to, listen for the train in the air. As it turns out, partisans in the Great Patriotic War in Soviet Union, World War II, known to you guys, actually used to do that. They would listen to German trains coming around the bends by actually listening to the rails. Then they would set explosives with some delay and run away. That was very effective. So this was the guerrilla war on the occupied territories in Soviet Union. And, it's sort of in the war movies, you can sometimes sort of see the partisans, listening to trains coming. The sound propagates faster. You can hear the train both from a longer distance because the sound propagates more effectively, but also comes to you faster, so you have a little more time to set up your charges and run away. Not you, hopefully. Don't set up charges on the American railroads. We are not in war. So sound propagates fast in solids. Now, the other quantity that describes sound propagation, the other important concept is the frequency, and I demonstrated to you these frequencies before. on the piano. The human ear actually, here's a picture of a human ear. Human ear is an incredible instrument, one has to say. If you were actually to build a model of a human ear electronically, it would be expensive and difficult to build. The human ear is characterized by two ranges. One is the frequency that you can actually hear, this audible frequency range, ranges from about 20 hertz to about 20 kilohertz, or a range of about 1,000. Actually, building a device that's sensitive to a factor of 1,000 in frequencies is not so easy. Well, you can get headphones now that sort of react to audible signals in that frequency range. Sort of a decent headphones, that cost $20 or so, will probably give you good sound in this audible frequency range. But, it took engineers, 100 years or so to build devices like this. It's not always easy. And the other place where the human ear is even more incredible is the fact that we measure intensities in the units of decibels, and the human ear is sensitive to intensities of about 16 orders of magnitude. And we'll get back to that in a second. So here's how the human ear works. The human ear collects the pressure waves from the sound in your ear, directs it to your eardrum, and then the eardrum transports, eardrum vibrates, this little membrane that separates your ear from the rest of the world, vibrates, sends the vibrations along the liquid in your inner ear to a various tubes, in particular to the cochlea. And the cochlea is a device that's sort of like a cone-shaped, rolled on itself, sort of looks like a some seafood object that I forget the English name for. It's sort of like a squid, but in a shell. What do you call a little seafood thing in a shell? I forget. So if you imagine it, take a cone and kind of roll it, and then fill it with little hairs. Those hairs vibrate and produce electrical signals that are sent then along the nervous system to your brain. The reason for the fact that the ear is this cochlea is shaped like a cone is important. The typical frequencies at which these hairs vibrate changes from the outer side where the diameter is larger to the inner side where it's smaller, and so different parts are then sensitive to different frequencies since the size is related to the frequency. And then the intensity of these vibrations is what you hear as the loudness, as the intensity of the sound. Again, incredibly interesting device. So you can hear frequencies from about 20 hertz or so. Again, if I were to demonstrate this to you on this tone generator, the very low frequencies sound like this. Oh, let me do a 40 hertz. This is probably the lowest frequency that can be audibly heard on this relatively old lo-fi speaker. And it sort of sounds like a mechanical vibrations. Frequencies even below this, you would probably feel with your entire body. Some people actually, I should have warned you, some people don't respond very well to low frequencies. Dogs don't respond to low frequencies well at all. Dogs can hear below the human cutoff of 20 hertz, and you annoy the hell out of them if you play something at the frequencies of sort of 5 to 10 hertz. This is known as infrasound. Frequencies below the human audible range that can be heard by other animals are called infrasounds. frequencies above the human range, so 15,000 hertz is probably the cutoff that sounds very high and annoying, like a sound of a mosquito. Frequencies above that are even more annoying, and the frequencies above 20 kilohertz are inaudible completely to humans. Frequencies above 20 kilohertz are called ultrasounds. Some animals will still perceive them. Bats communicate using ultrasound, using the effect known as the Doppler effect that we'll discuss in a second, or perhaps tomorrow. The perception range probably has something to do with the evolution. As I said, sounds are the typical sounds, so the typical vibrational frequencies various objects produce depend on their size. So if a big animal is coming to you, they probably produce sounds that are at lower frequencies. They're big, they don't vibrate very quickly, they produce frequencies that are low. The lions roar kind of at a low frequencies, the elephants produce low frequency sounds, so sort of the dangerous animals that can hunt us tend to produce relatively sounds of relatively low frequencies. Mosquitoes that tend to hunt us, drink our blood, but not necessarily kill us, produce high frequencies. The little objects produce high frequencies. The big objects produce low frequencies. This audible range is something that the humans have possibly evolutionally needs to perceive. But other animals, such as dolphins and bats, for example, that perhaps use sound for other means, for example, for navigation, have developed abilities to communicate at higher frequencies. For their evolutionary needs, that was perhaps important. So we characterize these frequencies. We actually break them into more ranges than that. If you are musically inclined, you know about octaves. We can play sounds. We subdivide each octave, each factor of 2 in frequency, into a range of 12 intervals. Each of them is specified by a particular note, A, B, C, D, etc., until F, right? That's 7, and then sharps or flats beyond that. Sharps or flats, right? No, sharps, right? The other one is flat on the other side. So that's each factor of 2 in frequency subdivided into 12 intervals will correspond to a particular node. And specific nodes are characterized by a very specific frequency. So, for example, we typically would tune pianos in such a way that this middle C corresponds to a frequency of exactly 256 hertz, and then the frequency that corresponds to C in the next octave corresponds to the frequency twice higher. So, for example, this is the middle C, and those of you musically inclined should be able to recognize how close I am to this tune. And the frequency twice higher would correspond to a C in the next octave. Frequency by another factor of 2 higher would still be a C, but yet in another octave, 1 octave higher than that. So each specific frequency, each specific key on the piano in different octaves would correspond to a frequency factor of 2 larger. So let me talk about intensity first, and then we'll talk about Doppler effect. How loudly you can hear the sound depends on how much energy each wave carries. And the fact that waves carry intensity, or carry energy rather, should be fairly obvious. Any mechanical motion has energy associated with it. We talked early in the semester about kinetic energy associated with mechanical motion. We talked about potential energy, energy associated with forces. So the wave propagation carries this energy along the direction of the wavefront. If I look at, let's say, that part of the string on the far right, at this point it's not vibrating, but I can make it vibrate by starting the oscillation on the far left. I start oscillation on the left, then at some point the string on the right will vibrate, the wave reflex goes back, goes forwards, and etc. So I can start deposit energy on one side of the string, and sometime later this energy will appear on the other side, the energy associated with mechanical transverse motion. So the waves carry energy forward. The amount of energy per unit time per second is associated with the power, and we describe the wave intensity as the power per unit area. The reason is actually relatively simple. The reason is that we perceive wave intensity as loudness. The area of our eardrum is about fixed. So we would perceive the vibrations, the loudness, as the force with which the air pushes on our eardrum. So we would perceive it as variations in the pressure. But if we want to compare the intensity quantitatively, we want to balance out the fact that my eardrum may be slightly bigger than your eardrum or vice versa. So we would normalize the force by the unit area. So effectively describing the intensity as the amount of energy per area through which the wave propagates. Another, the other phenomenon that's very familiar to you is the fact that as wave propagates, the amount of energy spreads over a larger and larger area, and the wave becomes weaker and weaker. In other words, sound of my voice as it propagates to you, if I turn my mic off, will get fainter the farther away I am from you. The amount of energy integrated over the entire area of wavefront is constant, but as the wavefronts spread out over distance, the area that they cover increases and the amount of energy drops. So as the area grows with distance, as distance squared, the amount of energy per unit area drops as 1 over distance squared, and effectively the wave intensity drops as 1 over distance squared. We measure this intensity in, we perceive it by how loudly the sound sounds to us, but we can also measure it more quantitatively in these units known as decibels. And sometimes you hear about decibels. If you go to a Sharks hockey game, there's these jumbotrons there, and they tell you to be louder when something good happens, presumably. And there are some numbers displayed on this jumbotron, and decibel units measure the intensity of people cheering. It's the intensity of the sound. Scientists use this logarithmic, so-called logarithmic scale. So basically, use the scale where the amount of intensity increases by a factor of 10 for each 10 decibels. The reasons to measure the sound in these units is because the human ear is an incredibly sensitive device. In fact, it is actually probably more sensitive than any electronic device that can be easily built. It has the sensitivity of about 16 orders of magnitude, or about factor of 160 decibels, which, if you convert it into the real intensity units, means 16 orders of magnitude, 1 with 16 zeros. The intensity is measured from the threshold of hearing, which is the faintest sound you can possibly hear, known or measured as 0 decibels, to whisper, that's about 20 decibels, to the pressure that's large enough to pierce one's eardrum, that's the intensity of about 160 decibels. Very loud noises, like at a hockey playoff game, could be 110 decibels. If you are unfortunate enough to be near the military jets, the intensity can be about 140 decibels. You see people working in airports wearing headphones to protect themselves from that force. Various mechanical devices can produce vibrations with the intensity anywhere between 60, 70 decibels to 100 decibels or so. So a very large range of intensities can be perceived by human ear. By comparison, a typical electronic device, kind of a hi-fi, if you buy a hi-fi stereo. What does it mean? It means high fidelity, means that it can produce sounds with very large clarity, with very large dynamic range, with very large range of possible intensities. For typical stereo, that range of intensities, from noise level to the loudest level it can produce, is typically about 80 to 100 decibels. And human ear is better than that. So again, incredibly precise and finely tuned device. Actually, at this point, before I quit, let me show you another interesting demonstration. So, I've been telling you that sounds is the propagation of pressure throughout the elastic air or another elastic medium. Here's how I would prove it to you. I have here a speaker that will produce a sound at exactly the frequency of a middle C, 256 hertz. And I couple this speaker through a so-called resonator device that will focus the sound wave on a little radiometer, a very light rotor built with very light foil vanes. And if I increase the intensity of the sound, if I can switch perhaps to the TV screen here, you'll see the sound wave produce pressure waves that will rotate these vanes. So again, this is an example of a transport of energy, transport of the pressure wave through the sound wave. There it is. If we eventually switch, can we switch to this camera, please? Not this one, next one. There it is. So here's this radiometer that starts going eventually. So again, a sound wave produces pressure waves that can be observed as mechanical motion. And your eardrums can perceive sounds much fainter than that and transform them to electrical signals. We'll discuss sounds and other wave effects, including interference and diffraction, on Thursday. And so you guys have a good break.